Okay, welcome to episode 3 of the Hardware VGA series. So in this video, I am going to give you a technical overview of the Readout module. I'll show you a simulation, which is how I gained confidence that the design works. I'll show you some experiments that I did on the bench to verify that it's working as intended. I'll talk about some potential trouble that we may run into, but there are some things that we might be able to do about it if we do encounter that particular issue, and then I'll go over some conclusions and talk about the next steps for the project. All right, let's get started. Since we're going to describe the design and operation of the Readout module in some detail, let's take a page from Curious Mark and enjoy some elevator music. The purpose of the Readout module is to generate the addresses of character and attribute bytes so that the pixel generator can use them to generate pixels and colors to send to the output module. In order to understand the design of the Readout module, let's first discuss the organization of video memory. The display controller uses the VGA 640x480 mode to generate a text display using a font with 8x16 characters. Dividing 640x8 and dividing 480x16 yields a text display with 80 columns and 30 rows of characters. Each displayed character is represented by 2 bytes, one for the character and one for the attribute value containing the foreground and background colors. That means that each row of characters requires 160 bytes of data. The total number of bytes of memory needed for the display is 80 times 30 times 2, which is 4,800. This is why the VRAM module uses 2 4KB dual-port RAM chips rather than just one. With only one 4KB RAM chip, which can only store 4,096 bytes of data, there would not be enough room for all of the character and attribute information. Each row of characters is displayed as 16 rows of pixels. The pixels are rendered on the fly by fetching the appropriate bytes of character and attribute information at the exact times they are needed by the pixel generator, with each block of 8 pixels being rendered from 2 bytes of data, the character and the attribute. So, the addresses of the bytes fetched for each of the 16 rows of pixels in one character row are exactly the same each time. The only thing that distinguishes the pixel rows in one character row from each other is the low 4 bits of the vertical count, which selects the correct row of pixels from the representation of the character glyph in the font ROM. Now that we know how video memory is organized, we can appreciate the essential function of the Readout module. It needs to be able to generate the correct sequence of video memory addresses for each row of pixels. It should start at address 0 in video memory for each pixel row in the first row of characters. Each row of pixels in the first character row is rendered by fetching the bytes at video memory addresses 0 through 159. After each pixel row in the first character row has been displayed, the start address for each pixel row in the second character row should start at address 160, and each row is rendered by fetching the bytes at addresses 160 through 319. The third character row requires fetching bytes starting at address 320, and in general, the memory fetches for character row I start at address 160 times I. The Readout module employs a relatively simple strategy for generating the video memory addresses for each pixel row. There are 2 registers, the row begin address register and the readout address register. The row begin address register, as the name suggests, keeps track of the address where memory fetches should start for the current row of pixels. The readout address register generates the address of the next data byte that needs to be fetched from video memory. For every row of pixels in a character row other than the first one, before starting to fetch memory for that row of pixels, the Readout module will copy the address in the row begin address register to the readout address register. This ensures that the last 15 pixel rows in a character row are fetched from the correct range of video memory addresses. Before rendering the first row of pixels in a character row, the current value in the readout address register is copied to the row begin address register. The idea here is that after fetching the data values for the last pixel row of the previous character row, the readout address register will naturally contain the video memory address of the first byte that should be fetched for the next character row. For example, after fetching bytes 0 through 159 in order to render a row of pixels for the first character row, the readout address register will contain the value 160, which is the correct start address for fetching bytes for the second character row. The row begin register has 2 control signals. The clear signal, when asserted, causes the value in the register to be set to 0. This happens before rendering of a frame starts. The load signal, when asserted, causes the contents of the readout address register to be copied into the row begin address register. This means that the outputs of the readout address register are connected to the inputs of the row begin address register. The readout address register also has two control signals. The increment signal, when asserted, causes the current value of the register to be incremented by 1. For this reason, the readout address register is implemented using binary counter chips. The load signal, when asserted, causes the contents of the row begin address register to be copied into the readout address register. This means that the outputs of the row begin address register are connected to the inputs of the readout address register. The outputs of the readout address register are sent to the display controller side address inputs of the VRAM module. So in general, the data outputs on the display controller side of the VRAM module will reflect whatever data byte the readout module wants to fetch. The control signals for the row begin address register and the readout address register are generated by a GAL device. The inputs to the GAL are clock and reset, the H-sync pulse begin timing signal, the horizontal activity begin and end timing signals, the low 4 bits of the vertical count, which are used to determine when data needs to be transferred between the row begin address and readout address registers, the vertical sync signal, which is used as a simple means to reset the row begin address register before the beginning of a frame, and the vertical activity signal. We will talk about activity shortly, but for now, all you need to know is that the horizontal activity signals allow the GAL to know the precise horizontal timing it needs in order to fetch data bytes from video memory at exactly the times that the pixel generator will need them, and the vertical activity signal lets the GAL know on which scan lines memory fetch activity needs to occur. Now, let's return to the horizontal activity timing. As we mentioned, its purpose is to make sure that data values are fetched from video memory at the exact times that the pixel generator needs them. A horizontal scan line consists of 800 clock cycles. The visible part of a scan line occurs between clocks 0 and 639. The horizontal sync pulse begins at clock 655 and ends at clock 751. Horizontal activity, meaning fetching data bytes from video memory and rendering them as pixels, must start before the beginning of the scan line in order that a block of 8 pixels and color information can be sent to the pixel generator at exactly clock 0 of the pixel row being rendered. Horizontal activity thus begins at time 791, 9 clock cycles before the first visible pixel in the next line is rendered. 9 cycles are needed because each byte fetched from video memory requires 4 cycles for a total of 8 cycles, and because the control signals are registered outputs, we need to initiate them 1 cycle early. Horizontal activity ends at clock 633, just before the end of the visible part of the scan line. At this point, all of the data for the scan line has been fetched, and the readout address register has been incremented 160 times. Now, let's consider how bytes of data are fetched from video memory. The GAL implements a 3-bit binary counter which counts from 0 to 7, then repeats. At counts 1 and 5, the readout address register is incremented. These times are the beginning of the memory fetches for character data and attribute data, respectively. Character data is fetched before attribute data because it needs to be fed to the font ROM in order to select a row of pixels from the correct glyph, which requires additional time. At count 4, the fetched character data is clocked into a character register, and at count 0, the fetched attribute data is clocked into an attribute register, and 1 row of pixels from the appropriate font glyph is clocked into a shift register. Note that these registers are part of the pixel generator module, so we will be discussing them in the next video. Because there are 3 clock cycles between the address increment and clocking the data from video memory into a register, and because clock cycles are about 39.7 nanoseconds, that means that the VRAM module has about 119 nanoseconds to yield a byte of data. Although incrementing a counter is not instantaneous, and we need to meet the setup requirements for the registers in which the data will be saved, so in reality we need the data to appear within 100 nanoseconds or so. The IDT7134 chips I'm using have an access time of 70 nanoseconds, which should meet this requirement comfortably. Similarly, time is needed for the byte containing the correct row of pixels to be read from the character ROM. I have flash memory chips with access times of 70 nanoseconds and 45 nanoseconds, so there should be plenty of time to meet the font ROM's timing requirement as well. This cadence, increment, commit data to a register, increment, commit data to a register, continues until the horizontal activity period ends. As long as we deliver the first character and attribute pair in a scan line at the correct time, we are guaranteed to deliver all of the character attribute pairs at the correct times. If you are thinking about this scheme carefully, you may have noticed a problem. We increment the readout address at count 1 prior to committing the first character byte to a register. If the row begin register is reset to 0 before the frame starts, this would suggest that the first character byte would be fetched from address 1 rather than address 0. To avoid this problem, we actually start horizontal activity at time 793 rather than 791, and start the count at 2 rather than 0. This effectively skips the first increment, the one we don't want, and allows the first character to be fetched at address 0. Data transfer between the row begin address register and the readout address register occurs after horizontal activity ends, specifically at the beginning of the horizontal sync pulse. There is nothing special about the choice of the beginning of the horizontal sync pulse, it just happens to be a convenient point before the beginning of the next scan line. The vertical count is incremented at the end of the horizontal sync pulse. You may recall in the last episode I mentioned that I made a hardware mod to increment the vertical count before the beginning of the next scan line, and we now know enough to understand the motivation for that change. Because horizontal activity, meaning fetching data from memory, starts before the scan line where that data will be rendered into pixels, we want the vertical count to accurately reflect the row of pixels within the character row that will need to be rendered. If we waited until the end of the scan line to increment the vertical count, we would be guaranteed to render the wrong block of pixels in the character glyph for the first column of characters displayed. Looking back at my failed attempts to implement a VGA text mode using an FPGA, I'm fairly certain I made exactly that mistake, so I'm correcting it in this project. Now that we have a somewhat detailed understanding of what the readout module is trying to do, let's take a look at the schematic. It's fairly straightforward. The row begin address register is implemented as two 74ACT273 devices. I chose the 74ACT273 because it can store 8 bits and it has an input that allows the contents of the register to be cleared. The readout address register is implemented as three 74ACT163 devices. As you might recall from episode 1, the 74ACT163 is a 4-bit synchronous binary counter. If you're thinking carefully, you might realize that we have 8 kilobytes of video memory, and 8 kilobytes is 2 to the 13, so we need 13 address bits. So, how do we represent a 13-bit VRAM address using 3 4-bit counters? The answer is that the GAL device actually maintains the high bit of the readout address register. I could have added a fourth 74ACT163 to implement the 13th readout address bit in a more natural way, and in general, I'm very much in favor of brute force over cleverness. But in this case, I just couldn't justify adding another chip just to implement a 1-bit counter. It actually didn't end up being too complicated to have the GAL implement the high readout address bit. It just needs to keep track of when the readout address is incremented or loaded and update a registered output appropriately. I won't cover the equations programmed into the readout module GAL in this video, but you can follow the link in the video description to check them out on your own if you're interested. You can also have a look at the simulation implemented in Logisim Evolution, which has logic circuits equivalent to the GAL design. Okay, so here is our simulation in Logisim Evolution. There is a readout module, there are hex displays for the row begin address and readout address registers. So I'm not going to go into a lot of detail about how the simulation actually works. I would certainly encourage you to download it and take a look yourself if you're interested. And of course, we've already had a very lengthy explanation of how the readout module works in general. So the main thing I would say here is that this simulator was really, really useful in validating the hardware design before actually prototyping it. This is really what gave me confidence that the basic approach was going to work, was viable. All right, so let's go ahead and run the simulation. All right, so reset is asserted, it's low. Let's generate a reset pulse, take it out of reset. I'm just going to set the auto tick frequency for the maximum and start it up here. So what you will notice is, okay, we are now in the first block of 16 scan lines that correspond to the first row of characters, and we are counting from 0 to 160. When we get to the end of the first character row, meaning once we're done with that first 16 row of pixels, yes, now the row begin address gets bumped to 160, and now we're counting up from 160 to 321. And at any rate, I have run this simulation and actually gone through an entire frame of activity, and in general, I'm pretty confident that the hardware design is reasonable and that, in principle, it should work. All right, so that's all I'm going to say about the simulation. So now let's look at the actual prototype hardware. All right, so here's the prototype of the Readout module. Again, point-to-point soldering on a proto board. I have tried as well as I can to do good decoupling of the power rails. So each IC has a 100 nanofarad decoupling capacitor. I also have a 10 microfarad bulk decoupling capacitor for the VCC and ground here. Here's the control gal. Here are the ICs for the row begin address. These are the load 12 bits of the readout address. Okay, so let's go ahead and try to do some experiments to see if this thing actually works and if it generates a reasonable series of addresses that can be sent to the VRAM. Okay, so at this point we're ready to test the hardware, and what I am going to do is I'm going to observe the output of the row begin address register using a logic analyzer. So because the number of bytes that are fetched per row of characters is 160, which is a multiple of 32, that means that the lowest 5 bits of the row begin address are always going to be 0, and I have verified that using an oscilloscope, so therefore we don't need to probe those signals. So what we will probe is the high 8 bits of the row begin address, and that is very convenient because I happen to have an 8-channel logic analyzer. All right, so the expected behavior that we're going to see is that the row begin address is first 0 at the beginning of the frame, and then 160 when we get to the second row of characters, and 320 when we get to the third row of characters, and so forth. In hexadecimal, that's 0, A0, 140, etc. You may recall seeing that in the simulation. So if we're only probing the high 8 bits of the row begin address, then what we should see is 0, then 5, then A, and so forth, and then 9-1 hex is going to be the last value that we should observe before the frame ends, and then at the beginning of the next frame we'll wrap back around to 0. All right, so here's our test setup. I've got all of the test leads attached to the correct pins on the ICs, and I have pulse view here from SIGROC set up to capture our data. So let me reset, okay, and then I will start the capture. All right, so it looks like we've got some data. All right, so we're going to need to add a parallel bus so that we can see the actual data values that are present on the row begin address lines. All right, so there's our parallel data. So let's see if that looks reasonable. Okay, so I think this matches our expectations. So there's a period basically after the vertical sync pulse when the row begin register gets reset that it's going to be 0, and then it counts up as the various character rows are progressed through, so we get 5, 10, 15, 20, and so forth. And then when we hit the highest row begin count of 9-1, which corresponds to, let me see, 1220 hex or 4640 decimal in terms of the actual row begin count, then that persists a little bit longer than a normal row because we don't actually reset it until we hit the VSync pulse, and so after that the count goes back to 0 and then we count up again. So I am going to very cautiously say that this looks like correct behavior. So this is a pretty exciting result because I think it does indicate that our readout module at least potentially is working correctly. All right, so here is the second test I want to do, and let me describe what is going on here. So I have the 6809 system hooked up, and I have the VRAM module installed, so that's pretty much the same as the setup from the last video, but I now have the readout module here, which is generating VRAM addresses that are sent to the display controller side of the VRAM module. And what that means is that there should now be data from the video memory being output by the VRAM module. And so I've wired up the connector on the carrier board for the pixel generator module, and that includes the 8 data lines that are coming from the VRAM. And so in this experiment, what I want to do is use the logic analyzer to just look at the data values that are coming out of the VRAM. And this is obviously the data that the pixel generator is going to render into pixels and color values that will be sent to the output module, which is not installed right now. All right, so I have run the VRAM test program, and that just puts increasing arbitrary byte values into each bank of the video memory. And so what I am hoping is that if I capture data using the logic analyzer, I should see those incrementing bytes that are coming out of the VRAM. So the way that the display controller talks to the VRAM is that the Readout module generates an address, and then whatever data is in the RAM should appear on the data outputs. There's no clock involved, and so we don't necessarily get absolutely, consistent data values from one byte to another. So there may be intermediate states that aren't valid data. We just need the byte to be valid after 3 clock cycles so that it can be latched into a register. But in general, we should see these increasing byte values. All right, so let's get the logic analyzer running here. All right, so here's our data. So this already looks potentially pretty reasonable. We get these blocks of data that correspond to horizontal scan lines. All right, and so if we actually dig into the decoded data on the parallel bus here, yeah, these do indeed look like increasing data values. So that is very, very good to see. So I think as far as I can tell, we are getting reasonable behavior out of the readout module and the VRAM, and I think this last pixel generator module is potentially all we need to get this entire thing working. So I mentioned that there was a potential problem on the horizon, and that problem is ground bounce. And the issue is that the 7.4AC and 7.4ACT logic series switch very, very fast from high to low and low to high, and this can cause switching noise, which inputs to devices could see as glitches. So I am definitely not an engineer, and I really don't know anything about the analog characteristics of high-speed digital circuits, so please take everything I'm about to say with a grain of salt. But basically, from what I've read, these logic series 7.4AC and 7.4ACT are notorious for being a little bit tricky to work with. So here is a forum post that I found that mentions these issues. I can also share that I have seen examples of strange voltage spikes on inputs of devices in this circuit. So I'm definitely a little bit concerned about the potential reliability of this design. So the good news is that there are some mitigations for these problems. So power supply decoupling is really important for these kinds of high-speed digital circuits. I've also read that avoiding long wires will help, and having a good ground plane will help. All of these are going to be more feasible when we have an actual printed circuit board rather than my crazy, janky, hand-wired prototype. Another potential mitigation is to put a series resistor on the outputs of these devices to prevent them from switching as hard. I'd kind of like to avoid doing this just because it would be more components in the design and more board space on the PCB, but it is an option if necessary. Finally, there are other logic series that we might use in this design, such as the 7.4AS and 7.4ALS series, so that would be another thing we could experiment with if this problem does crop up in practice. So at this point, I don't really know whether this is going to be a serious issue for my design, but I'm pretty sure that we will find out one way or the other when we finally assemble the complete system by building the pixel generator and test it, and if it works, great. If it doesn't, we have some things that we can try. All right, so in conclusion, the Readout module seems to be working, although I'm not 100% sure if it's working, but we'll find out soon. So the next steps are to finalize the design of the pixel generator module. I definitely need to do a simulation of it and make sure I'm satisfied with the results of the simulation. And then once that's done, we'll build it, add it to the prototype, and see if we have a working display. So that will happen in the next video. So I will see you then.